Okay, welcome back. So I'm here to give another bit of feedback on the next lecture of James Elias's inductive course in physics. So let's jump into that. This is lecture 2, an inductive summary of physics by Professor James Elias. So we'll get going on this right now. We're going to basically cover it the same way we did last time, except this time I'm going to jump directly into the different integrations he possesses. The general approach I've already more or less fleshed out. Okay, so integration 10 was Galileo's law of motion. So this thing basically begins with the idea that the heliocentric model, as initially proposed by Aristarchus, leaves some things to be explained. Namely, the biggest one is, why don't we feel this motion? I mean, it feels like we're stationary, so why don't we feel it? Now, the basic question is that Galileo was ultimately able to ask in regards to this was, well, why should we feel planetary motion? And the original answer was, well, that's, we can feel when we're in motion. You go on a horse, you go on a ship, we can feel when we're in motion. And so the investigation basically proceeds with a series of back and forth questions. I'm not going to go over all of them, but ultimately the purpose of this investigation was to kind of reconceptualize motion, and this was quite important in this initial context because the way that motion had been conceptualized before this is that there were two categories of motion: natural motion and violent motion. And natural motion had a whole bunch of different things, like there were natural forces of gravity and levity, and gravity pulled earth lower than water, water lower than air, air lower than fire, and levity raised fire up higher than all the others, air, not, above water, water above Earth. So it was this kind of interplay between gravity and levity. And then they thought there was also natural motion of the heavens, which was this orbital motion that is observed on a daily basis. So that was basically how this investigation went, until it came to the conclusion that you don't need to have a cause of motion, that objects in motion will just kind of continue to move as they were unless something comes along and pushes on them. So this is basically a discovery of the law of inertia. Now, it's not categorized this way. Professor Elias doesn't categorize it this way just yet, so I have a question about that later. But first, some things I thought were memorable about it. I really did like the examples of testing inertia. So, playing catch in a moving vehicle, we all are aware of this, that the ball is not like the movement of the object leaves the ball behind if you're playing catch. There's also a ship where Galileo apparently climbed to the crow's nest and dropped the bag, and it fell basically at the post of the mast. It wasn't like the ship kept going and the bag fell towards the back of the ship or even off the ship. So I thought that was interesting. Then there's also a discussion of slowing as due to contact between different objects. That something slows down if there's more rubbing or contact. I thought this was a good indicator for the idea of contact forces, and basically this is how we generally expect forces to interact. We expect them to have to make contact with one another. That's going to be a big thing, and ultimately an apparent exception. Gravity being an apparent exception, along with some of the other essential forces. So definitely thought that was interesting. Some questions I had. I do think this could really benefit from some kind of example. So Galileo's cradle. I believe Galileo actually did the experiment of a Galileo's cradle, basically showing that no matter the angle of two sides of a little dip for a ball to roll down, it would absent friction, once you eliminated friction, it would basically move to the same height that it started at. Now, you can never completely eliminate friction, but but Galileo would eliminate more and more friction and notice that it would get closer and closer to its starting point as that happened. And then he generalized this to say, well, if we start the ball up high and then there's no slope on the other side, then there's no reason it should ever stop absent of friction. So I thought that's an interesting example that I think could help flesh this out a little bit more. And then just sort of bring in some real world experience. How when you take the time to eliminate friction, either like on an air hockey table or an air puck, you do get this sense in which the smallest nudge can just get these things to keep on moving until they bump into something on the other side of the room or on the other side of the table, as the case may be. And then the concept of inertia. I was just curious if there's a reason why this is or is not brought up, or specifically is not brought up in this case. I know, from what I understand, Galileo did not use the concept of inertia, so maybe that's why. But just in terms of an inductive presentation, is this worth bringing up at this point? Next integration was the phases of Venus. Basically, the motivation is that if we start looking at the other planets, maybe we could provide evidence of heliocentrism, the evidence that this model is the correct model. And so the question is, are the phases of Venus consistent with this heliocentric model? The investigation is Galileo looked through his telescope and found that the answer was indeed yes. And this means that Venus goes around the sun and not the Earth. So some good things about this one. I like the way that learning about the phases of the moon ultimately continues into other realms, and then is useful in improving something we do take for granted, but was a pretty advanced conclusion for its time. Questions I had. From my understanding, the geocentric theory would involve phases of the planets as well, and this is sort of implied in the lecture. What I would ask is, what phases would you expect to see if the geocentric theory is correct, and then what phases were seen that kind of prove the geocentric theory couldn't be correct? And my understanding is, given the positioning of Venus, given that it's leashed to the sun, you would, if both were going around the Earth, you would only ever expect to see, Venus in like a crescent or a new phase. So very similar to how when the moon is close to the sun, it's always in its crescent or its new phase. Now, the fact that we observe full and gibbous Venus basically means that in order for Venus to get full illumination, it's got to be on the far side of the sun. So that's my understanding of it, but I think this could benefit from the contrast. So what does it actually mean for the phases of Venus to be consistent with heliocentrism? And then I think this could really benefit from some images. There are some good images of the phases of Venus just in the common images of Wikimedia. And showing that not only do the phase change, but the size changes as well. So when you have a new Venus, it's significantly larger than when you have a full Venus, meaning, new Venus is on the near side of the sun, Venus is on the far side of the sun. So that's why you get that large apparent change in size. 12 was the structure of the heliocentric model. Okay, so starting off with the motivation is that observation should be able to reveal more about the arrangement of the evidence. It should be of the heavens. It's a typo on my part, but I'm not going to stop it at this point. So we asked the question, what is the arrangement of the heavens in the heliocentric model? Like, which planets come first, second, third, so on and so forth. So not going to go too deep into this one. Basically, this is two sort of separate investigations, one for inner planets and one for outer planets. The inner planets are significantly more simple because because just by looking at the maximum distance away from the sun, can you basically set up a trigonometric relationship. The outer planet analysis requires a bit more work. It requires determining the length of the planet's year, which you do by measuring the time between oppositions. It's covered more in the lecture. And it requires this sort of this measuring of time in between when the planet is in opposition and when it forms a 90-degree angle with the sun. So 2 different analyses, but ultimately using both geometric and trigonometric relationships to determine the radii, the orbital radii of these planets. And from there, you can get the distance of all the planets from the sun. Now, this is all the observable planets, which basically stops at Saturn. So Uranus, Neptune, and Pluto, which is of course no longer a planet, we're not included and not measured at this time. Took a while to discover those. So some memorable aspects. I really liked the mix of trig and geometry to prove this physical phenomenon. I think this is a good way to show the application of those skills. I think it's awesome. Some questions I had. Why do the interior planets appear least to the sun? So this is claimed in the lecture, but I think this would be more clear if there was like a visual example. So given that the orbits of Venus and Mercury are interior to Earth's orbit, why does it make sense that they would never appear to venture very far away from the sun in the sky? So I think you could benefit from that. I was also curious. This is something I don't actually know, but how given, especially when we're interested in measuring these things precisely, how is opposition measured? I would be curious to know that. And then last thing I thought was pretty funny was the Pluto joke that Professor Elias makes. He says Pluto, as I said, is not a planet anymore, and then in a very deadpan way says because NASA blew it up with a rocket. I laughed out loud for quite a bit at that point. That is, of course, not why Pluto is no longer considered a planet anymore. But thought it was kind of funny. And then one other thing I think in this lecture we're told that under the geocentric model, it takes the sun 365 days to go around us. That was not my understanding of the geocentric model. So my understanding of the geocentric model was the sun and all the heavenly bodies went around the Earth on a daily basis, and the progression of a year was, in astronomical terms, was basically how long it took the sun to migrate its way through the ecliptic. So, and the ecliptic was associated with the season. So when the sun was in different constellations of the ecliptic, it would you would have different seasons. So again, when the sun was in Scorpio, Capricorn, Sagittarius, you got the cooler months. When the sun is in other constellations, you get different seasons. So that was my understanding. All right, moving on to the next one. The sun is the cause of planetary motion. So the idea here is if the Earth is not the center of the universe, if the sun is, there's got to be a reason for that. Maybe there is super advanced civilization living on the sun chosen by God, but let's look for natural reasons why the sun might cause heliocentric motion. So what causes the heliocentric model? Or what causes heliocentric motion, I should say? The model is a human conceptualization of the observations. So basically what is done here is you calculate the orbital speed from the period of the planet's rotation and from the and from the orbital radius. So you take the circumference, treat it as a circle, divide by the period, and you get a speed. And we see a decrease of orbital speed of the planets as distance increases. As distance increases, orbital speed decreases. Now, we don't have the mathematical relationship yet, but this leads to the conclusion that the sun causes planetary motion. So, I did like the introduction of speed, radius, and period, just in terms of a mathematical equation. These are all things that come up again in kinematics, so introducing it at this point, very useful. Some questions that I had. Is it proven that the sun is the cause? Now, it definitely proves that there's something about the sun that is relevant there. But because the mechanism isn't clear, I'm just curious if it's actually proven yet. Now, the counter argument to that is, well, if it's not the sun, what else could it be? Like there's no, given that the sun is the only major body we have a pattern for here, what else could it be, if not the sun? And that's a good point, but I guess that's my question is what does it actually take to prove it? So moving on to Kepler's third law. This was integration 14. We know the sun has something to do with the orbits, so how exactly is it that the sun is causing planetary motion? And so basically what Kepler did here is he plotted the period versus the distance away from the sun, or the orbital radius. So I've got d, but often it's written as r. And the conclusion he came to is that t squared is proportional to d cubed. So t squared is equal to some constant times d cubed. Some things I liked about this. I liked the idea that quantification is the next step to determining the relationship. So we saw that, when we calculated all the speeds in the previous integration, we saw that that there was a pattern for sure, but we don't really know the relationship. So the next step is to compare relevant quantities and see what their relationship is, and this does give us Kepler's third law. So the main question I had here is the technique that would have been used. Now, even if this wasn't the technique that Kepler used, I think linearization is just an incredible method to use in this particular context. So what I mean by linearization is I doubt the plot of t versus d, of period versus radius, would give you what you are after. It would definitely appear to be polynomial, but it wouldn't be clear, kind of what that meant. However, if you plotted t squared versus d cubed, that would give you a straight line. And that would basically tell you the powers, the exponents on each of those quantities in this relationship that you had. So this is something that I taught a lot in my physics classes, just as a technique of determining relationships. You can figure out the nature of the relationship and saying, oh, it kind of looks quadratic. Well, you can actually test that. You can test that by squaring one of the quantities, in this case, then cubing the other quantity, and then plotting those together and seeing that the t squared versus d cubed does give you a linear relationship. So it's a very useful technique, and wouldn't surprise me if it was what Kepler did, although I don't know that for sure. Okay, so the 15th integration. Jovian moons obey Kepler's third law. The idea here is that with a telescope, you can observe this cluster of stars that's always in the vicinity of Jupiter, and leads to the natural conclusion that these are very likely moons. You wouldn't have these, since they're always near Jupiter, they've got to be associated with Jupiter in this way, and they are, of course, the Jovian moons. So the question then is, do these moons obey Kepler's third law? So basically what is done here, you measure the relative radii. So it's hard to, using the telescope, get the absolute orbital radii of these moons, but you can get it in terms of, say, like the diameter of Jupiter, something like that. And then you can get the period pretty easily just by counting, how many days it takes the moon to get back to where it started relative to Jupiter. And when we plot these, we see that, yeah, t squared is still proportional to d cubed. So Kepler's third law is obeyed here as well. So I really liked the that this example is, it's you definitely, you can't see these Jovian moons with the naked eye. You need to use the telescope. But when you do that, you can show that Kepler's third law is a generalization. It's not just something that happens to be true for our solar system. Anytime you have the situation with objects orbiting around bodies, it seems like Kepler's third law is going to hold, at least in some context. I also like the way in which, even though from our current context it's kind of obvious that this is being caused by gravity, this is not an obvious explanation at this point. Among other things, gravity basically pulls things towards one another. So how could it cause orbital motion? And this isn't quite a clear question yet. So I did like that caveat there. So the questions I had, I wasn't quite sure what is meant by prove an ellipse in this context. Professor Elias mentions that he's not quite sure how to prove an ellipse. So I don't know if the question is he's not able to prove what an ellipse is, or he's not able to prove that the orbits were elliptical. From my understanding, the orbits were proved to be elliptical when it was noted that the very precise observations that Tycho Brahe made, who was Kepler was his protege. The very precise observations he made, they didn't quite fit with circles. It was just a little bit off. And these observations were very good, made over, decades, and compiled observations even longer than that. And it was always just a little bit off. And I believe it was by using an ellipse that Kepler could actually get the data to match up. So I don't know that this was. I think this was more an example of curve fitting. I think the proof that it should be an ellipse comes ultimately. I believe that comes with the law of universal gravitation combined with the initial conditions of the body that's in motion. So I think that's how that proof comes about, if relevant. I also think this is a really interesting time to pose a challenge question to the class. This is me coming at it from a teacher's perspective, but one of the integrations that we've already covered in this lecture gives a partial answer to that gravity question. That would be the law of inertia. And Galileo had a partial answer to that. He just didn't really realize it yet. And this is one of the things that ultimately blocked him from creating universal gravitation, and it would be, the topic or the task of our next hero to come along and show that, this idea that Galileo came up with actually proves why gravity is able to cause this effect. So you don't give the answer away just yet, but it's an interesting thing for students to think about, to say Galileo's actually already got a partial answer to this. He doesn't realize it yet. So put that into your mind and think about that. Okay, integration 16. The moon is a world like this one. So the idea here is we know the moon's a sphere, but is it like a marble just out there in space? This kind of perfect sphere. And the question is, does the moon have features like the Earth's? The investigation, that should have been the conclusion, but the investigation was you basically look at it with a telescope, and the conclusion is that indeed, yes, it does have geographic features like the Earth, in particular mountains, craters, things like that. So I like the focus on shadows here, and basically it's, even looking at the moon from very far away, it is somewhat hard to tell. You can tell that the colors are not uniform, but it's only really by looking at the shadows that you can really see the way that the surface is kind of pitted and marred. So interestingly enough, the painting that is presented in this lecture of Galileo showing his discoveries to some Catholic priests actually is a drawing of the moon that he made of the moon, a sketch of the different shadows and things that he saw when looking at the moon. So zooming in on that could be really useful. Another aspect is that giving a close-up of the images of the moon, you can really see when, you can see shadows. You can basically see shadows near the terminator. And that gives you a real sense of the features of the moon when you can see those shadows. So zooming in on a moon that's in a quarter phase, like through a telescope, it would give a very poignant visual example of this. So last integration is the period of a pendulum. Motivation basically starts with Galileo being bored in church and measuring the swinging of different chandeliers that were kind of going back and forth. And the question he asks here is, does the pendulum depend on the amplitude? So does the period depend on the amplitude? So does the time it takes for one cycle of the pendulum depend on how far you pull it back? And there's a reason why you might expect that it would, and a reason why you might expect that it wouldn't. Basically, the investigation is to actually do the experiment. And finally, we see that the period does not depend on the amplitude. Basically, the increased distance that the pendulum is required to travel, that the pendulum bob is required to travel when increased by the amplitude, is offset by the fact that it gets going a lot faster, that gravity pulls it down, gets it going a lot faster. So that's one of the things that's going on there. Some memorable aspects of this one. I like the description of Galileo as a bored kid. I can just, thinking back to some of my own childhood experiences, I can just remember just looking up and just, imagining and kind of daydreaming in my head and in those kinds of situations. I thought that was funny. Some questions I have, seems like a good time to ask, well, if the period doesn't depend on the amplitude, what does it depend on? And given that this is an experimental question, is there value in pointing out that, okay, we can actually do this experiment? It's not exactly like looking at the heavens where we kind of have to go out and observe and maybe wait for the right opportunity to present itself. We can actually go into a spot and deliberately make the kinds of observations we want to make. So we don't have to wait for, things to change about the chandeliers. We can actually go make our own pendulums and do the experiment ourselves. Some questions about the reading assignments and quizzes. The practice and quizzes seem to be answerable from the lecture content alone. It's generally how I prefer to present classes. In that case, I'm just curious about the purpose of the reading. Is it to is there additional material that you want the students to get from the reading? Is that for students that didn't quite get it all, would prefer to read, didn't quite get it all from the lecture? And then in the questions, both on the practice and the quizzes, it seems like the purpose is primarily to again sort of repeat the integrations, use the integrations in a different context. And I'm just curious if there's any other purpose to the questions. Like, for instance, or if there could be any other purpose to the questions. Like, for instance, giving them sort of a geometric puzzle that might be relevant to answering a set of upcoming integrations. So the kind of example I think of is you could have prior to this lecture you could have just asked some qualitative questions about how far planets have traveled in between when they're in opposition and things like that. So I'm just curious if the questions themselves can be used to prime the students for the upcoming integrations. Lastly, again, the purpose of the reflection writing, just still not sure if this is for the student or the instructor. Maybe not a particularly relevant question, but just as a teacher, I'm kind of curious about what is the goal behind that. So that is all I have for the summary of this lecture. So thank you for watching, and I will see you the next time I present one of these.